Once again, welcome to this GENI webinar. My name is Ben Newton. I am a graduate student at the University of North Carolina at Chapel Hill, and we've been so honored to host these webinar sessions. They have grown in popularity over the months, and we're glad to see so far 18 participants here, which is almost the maximum we've had so far. But we also are really excited that the videos are becoming fairly popular. I think more people have watched the videos than have participated in the live sessions. So we invite everybody to go back and look at the videos from the previous sessions as well. It's my honor to introduce to you three experts in GENI Wireless. Yvonne Seskar is a faculty member at Rutgers University. He's the Associate Director of Information Technology there, and the PI of the GENI Wireless program. He received his master's degree from Rutgers University and has been there since 1991. Manu Gosain is a systems engineer for the GENI project office. He has been with the GPO since 2010 and has an MS in electrical engineering from Tufts University. And also my pleasure to introduce to you Mike Sherman, who is a staff member with WinLab, and he will be helping to direct the demonstration. And he is also a graduate student at Rutgers University. So it's my pleasure to now turn the time over to Manu Gosain, and he's going to start out by giving us a presentation about wireless in GENI. And after that, he's going to turn the time over to Yvonne for the rest of the presentation and the demonstration. So Manu, we'll hand it over to you.
Okay, thank you very much, Ben. So are my slides visible? Okay.
Yes.
Perfect. Okay, so what I wanted to do is the agenda for this talk, it was sent earlier by Ben, but I just wanted to recap what we'll be doing today. I'm going to be giving a brief overview of the GENI wireless ecosystem in terms of the deployments, what sort of wireless technologies are available, what sort of GENI aggregate manager software that's been developed for the wireless domain, which is a little bit different, as you can imagine, from the wired GENI racks and the other webinars you might have attended. So there's a little bit of a difference. I'll also be giving you a quick overview of how to access these wireless resources from the GENI portal. So with that, I'll just really briefly recap GENI architecture for those of you who might not be regular users of this testbed. So just to clarify some basic core concepts and ideas, give you a very brief overview of LTE. And LTE is basically, could be an entire seminar on its own, but I just want to highlight some main terms so you can keep abreast of the demonstration that Mike and Yvonne will give in a little bit. Talk to you a little bit about our research motivation on why we want to investigate and have LTE and wireless be part of GENI, and then basically talk about what exactly the resources are available at the various GENI sites. So basic GENI network architecture, the goal was, or the goal still is to have a flexible network and cloud research infrastructure. And the basic units of resource that's available in GENI is called a GENI rack. And as you can see, we'll build our way from the left to the right. So at campuses, there are resources which are called GENI racks, which is basically a data center type resource, which has plenty of compute server nodes, a programmable open flow switch, and then it has connectivity on the data plane into other racks that live upstream in regional networks. So from a campus in a particular university, all the way up to a regional network, and then all the way into a research backbone, which in this case is Internet 2. One of the main things that we differentiate with is the blue and the orange lines on the diagram. The blue lines are the layer 3 control plane, which is a channel that allows you to access GENI resources over IP and allows you to SSH into these resources. And the orange line is the data plane, which is where the real fun happens, where the concepts of programmability and slicing are implemented. Where does the wireless piece fit into this puzzle? On certain campuses, around 16 as of last count and continuing to grow, we have wireless resources in the form of WiMAX and LTE base stations. And these have been connected over the data plane network directly one hop from these GENI rack resources. So what you now have is a complete wireless edge ecosystem in the form of LTE and WiMAX base stations and compute and storage resources on campus, on site. And all of this is available to you via the GENI portal and the GENI resources. And again, the applicability for this particular ecosystem is not only for network research, but also for application domain, such as cyber-physical systems, vehicular networks, and other domain sciences. This is sort of, again, a refresh of the current GENI deployment. As you can see, we have about 12 to 14 different wireless edges, which are shown here. And we'll be working with the Rutgers InstaGENI rack, shown in green if you look up towards New Jersey, and we'll be using an LTE base station that's been deployed there. So just to give you a quick overview of what LTE is. LTE, as you know, is the current de facto 4G standard that's been in use. So there's obviously a lot of really nice synergy with doing research with things that are being in use in industry and have certain challenges that can be addressed by the research community and students like yourself. So some terminology. eNodeB, which is also known as the evolved NodeB, is basically the base station. So this is the actual hardware that you might have seen deployed on the sides of buildings, on rooftops, driving along highways. So that's basically the base station, which, you know, it's just called the eNodeB in LTE speak. It has certain functions such as admission control. So it allows who can connect to that base station and to the network. And it has plenty of configuration and provisioning options that you'll be seeing shortly in the demonstration. The Evolve Packet Core is basically the core set. So if you look at that highlighted rectangle on your left, all the components within that are combined, called the Evolve Packet Core. And then the main components, so are the mobility management engine, which there are a lot of. This is another component within this Evolve Packet Core. So now we're talking in terms of
recording is on.
Now we're talking, sorry, I'm hearing some echo. That's okay. Hopefully it's clear enough. Okay. So the mobility management engine here is the first point of connectivity that is established between the eNodeB base station and the core service, which in our case is going to be running on GENI racks. So think of a fiber or an Ethernet connection that sends all the radio messages received by the eNodeB. And this is the mobility management engine is the first place where all of these control messages are sent to. A service gateway and a packet gateway are essentially just gateway elements that allow you to connect to the actual packet data network. And the HSS is the home subscriber server, which is nothing more than a database that has information about the different IMSI, which are the SIM cards, which are authenticated or are allowed to connect to this network. So another piece to highlight are the dotted lines are essentially signaling traffic, and the solid line is basically the data plane traffic. The way a UE or a client connects to the internet once it instantiates a connection is that after all these messages, the control messages are set up in place, you end up with a GTP tunnel all the way from the base station where your UE is connected all the way to the packet gateway. And this GTP tunnel carries all your traffic packets directly. So there's a tunnel that extends all the way from the base station, eNodeB, all the way to the packet gateway, and then the packet gateway basically has connectivity out to the internet. So keep in mind there's signaling, control, and data traffic, and in our case, we'll be doing lots of cool stuff on this data side. Any questions so far? Okay, I'll continue onwards then. So this again, this is I like to keep this picture here because I like to highlight how complicated and how complex the LTE protocol itself is. This is essentially just showing an attach procedure when a UE comes in range within a eNodeB and tries to connect. So between the time the UE has sent its first request to connect to the eNodeB and the LTE network to the setting up of the actual tunnel and the data being transferred, you have this entire set of messages. And again, we don't need to go through it, but what I want to highlight here is the complexity that this protocol and the standard has. And that's why there is a strong motivation for us to provide the capability within GENI for you to be able to investigate these really difficult protocols here. And majority of the work is already done for you in GENI, so you don't really need to worry about most of this. Another couple of motivating slides. So just to drive home the point that LTE is pretty complicated, we have lots of S-X messages that flow between all these elements: the mobility management entity, the service gateway, the packet gateway, to set up the data paths, i.e. the tunnels from the UE all the way up to the packet gateway. And if you're trying to move without a handoff from one base station to another base station, you have 33 control messages that flow across these three elements within the evolved packet core. And if you are changing a mobility management engine entity, then there are even more messages. And similarly here, you have, if you're doing a paging request from a UE, if you're waking up from the data plane side on the handset side, you basically have about 15 to 19 control messages between the packet gateway, mobility engine, and the eNodeB. So basically, this is the main research motivation for us. We also want to keep an eye towards the next generation cellular and core network systems, which are really cool concepts such as cloud radio access networks, 5G networks, virtualized evolved packet core, and mobile SDN. Some of these concepts have already been implemented in industry and already are out in the field. So it really allows us to provide a nice ecosystem for researchers to use this. And we have a campus kit for a very reasonable, amount that allows for turnkey access to turn on LTE technologies at your campus. So if you are interested in hosting LTE at your campus, please do reach out to me after this webinar. This is basically commodity hardware that we acquire and provide to each campus. We use a base station from Airspan Networks. It's called AirHarmony. It's a form factor which is much smaller than a macro cell, so it's not a really, really powerful transmitter. It's only 2 transmitters, maximum transmit power of 5 watts. And it runs a flavor of LTE, which is based on time division, not frequency division. Implements a MIMO technology on the antenna path, and operates on band 38 and band 41, which is where all GENI wireless equipment lives, in the 2.5 to 2.7 gigahertz space. We have multitude of UE equipment from Android handsets down to USB dongles with Linux drivers, and we also provide test SIMs, so you don't really end up interfering with commercial service providers. This I'm just going to skip over. This is basically what a site might need. So if you are interested in an LTE deployment, these are the steps you might need to take on your campus to get everything set up. So this is just more for edification purposes. And this is what the LTE campus deployment at the campuses shown earlier sort of looks like. we will hear shortly from Ivan about the orbit management framework, which basically is the GENI resource manager that controls all of this. But what we have is GENI resources in the form of GENI racks, LTE base stations, and this is all, as I said earlier, hooked up on the data and the control plane. And these yellow boxes that you see here are nodes that are developed by WinLab, Rutgers University, and distributed out to our different GENI sites. And what this allows you is the ability to, for folks who don't even have these resources on their campuses, they can remotely log in to these resources to use fixed clients with connecting to the LTE base stations at the different sites. So if there is not a mobility-oriented application, but you're just trying to understand the LTE standard, you can log into these resources remotely. And again, there are data and control channels that allow you to access these resources over layer 3 and then program everything on layer 2. So with that, I'll again pause for questions. And if not, I'm just going to show you a quick demonstration of how to access these resources via a GENI project and through a GENI portal. So bear with me while I just switch applications. Okay, so do you see my home screen on the GENI portal?
Yes.
Yes. Okay. So this is sort of what an average user is going to see. So if you were to use if you wanted to use wireless resources, you would basically just go under the partners tab and click on the Orbit URL. What this does is this, and then you press login. And all of this has been documented, and I will provide sort of a bibliography of the various wiki pages that we have that allow you to do this at your own pace. So for now, I'm just trying to show a quick demonstration. And again, the beauty of GENI is you always have a single account, and it asks you if it can share the information with this testbed, which is living at the Orbit WinLab over at Rutgers University. And at this point, you now have access to different sorts of wireless resources that you might require for doing your experimentation on GENI. Since wireless research, a lot of people do not like to have interference and noise of other experiments going on, the testbed is time sliced, meaning that when you want to make a reservation, you will get the entire testbed and all its resources just to make sure that you're not. And this could be an entire institution, and then you can have multiple users accessing the system with the core functionality of using GENI slicing and programmability. But in terms of who's using the testbed, we like to have a single authority and single point of contact so that other people in his or her project can access all those resources. So this is sort of a quick highlight of how you would end up making a reservation. As you can see, we do have currently a reservation for a project that has been already created on the GENI portal, and Mike will very shortly demonstrate the resources that we've reserved on this Orbit testbed that will allow you to use this for GENI purposes. So with that, that's all I had to start off with, and I think at this point I can release the screen and pass it off to Ivan. So Ivan, would you like to take over?
Sure, yes, we can take over. Let me just make sure that we are on the...
Please share the screen.
Share the screen, please. There you go. Okay, so I hope you see the slides. So continue where Manu stopped, just to sort of point out. In addition to an airspan base station, one of the things, as Manu mentioned, that is really getting a lot of traction these days are these software-defined radio-based approaches to wireless research. And as part of GENI Wireless, we do have two more base stations, eNodeBs, that are purely software-based, and those are these two middle columns, Amarisoft, which is USRP-based SDR implementation of LTE, as well as OpenAir interface, and SRS LTE, which are the other two implementations of LTE standards that are done in software. We also have an IP access base stations, which are these femtocells that we support, but I don't think there is a single site that actually makes it available. I believe PhantomNet does. So in other words, in addition to big base stations that are deployed in the outdoors and various campuses, we do have a lot of other research infrastructure that's focused on LTE. Now, as Manu mentioned, we do have, we did one thing with the official base stations that we have on various campuses, and that is we wrap them up with the software that enables us to manage and control base stations as the experiment is progressing. And so you can see on this particular slide two ways of dealing with the one with MyMax, the other one with LTE, where we are sort of trying to abstract the way one approaches the base station management. Ideally, of course, we want also to have an SDN-based data path, and that's what we did for both WiMAX and LTE. So you're not forced to use the EPC as such to inject your traffic into the wired network to which the base station is attached. However, you have to remember that this is a sort of a research topic and ongoing research, and therefore these capabilities are not necessarily something that first-time experimenter would want to play with. However, we do allow in all the installations ability to replace these components, these data path components, with something that's part of your own experiment. Now, Manu mentioned that we have the aggregate manager that's managing the base stations, and we named this one BS control, and it's used for management of both the base station as well as a core network or EPC. And it's, as the slide implies, it's based on REST API, which means that you talk to the aggregate manager for the base station through the HTTP requests. And they're fairly straightforward, simple HTTP requests that allow you to change any of the parameters of the base station as well as EPC, and to configure it, tune it, even to some extent treat it as a platform to implement various control algorithms on top of it. Now, of course, as you can imagine, the ability to implement these controls is somewhat limited with the number of functions that we implemented on top of it. Obviously, this is all open source, so people are more than welcome to extend this with additional functionality at any time. Now, I just want to spend some time talking about the open source implementations of LTE that are based on software-defined radios, mainly because this is a very interesting platform for people to customize LTE, and it's pretty much the only way you can fully modify and play with LTE standards, right? Of course, commercial base stations provide nice coverage on campus and allow you to connect and have a decent performance. However, these are still closed boxes with proprietary interfaces, and of course, we can't modify the software running on the base station itself. The SDR platforms, and we have actually 3 different SDR platforms in various stages of maturity. OpenAir interface, which is the one that we will demonstrate today, SRS LTE, which is mostly focused on UE or client devices implementation of LTE, and OpenLTE, which is literally a library of functions that allows you to build various pieces of LTE standard. Are software-defined platforms that are running on commodity PC. And then, of course, given that we have in all of the deployments, or GENI deployments, we have commodity PCs sprinkled either in the rack or in the yellow nodes. That means with the appropriate addition of SDR front end, one can easily implement both client and fully programmable client and base station using one of these open source implementations. Now, OpenAir interface is interesting because it's a full source implementation, full open source implementation of LTE that includes all three major components, the eNodeB, the UE, and the EPC. And actually, this slide shows you the partitioning of functions and literally the way we are using OpenAir interface in Orbit Testbed, and of course, it similarly could be used in other deployments to play with various aspects of LTE. And for instance, this platform was also used to implement LTE-U, as well as attempted at LTE-AA, which is the other unlicensed implementation of LTE. Now, as you can see in the bold, this platform, the beauty of this platform is that you can actually use commercial devices and commercial EPCs and commercial eNodeBs in various combinations with the open source implementations. And highlighted or bolded combinations are actually ones that are readily available to play with in GENI, right? So this is pretty much just a very brief overview of components that we'll be using today in the tutorials. And at this point, I want to switch to give the mic a mic, no pun intended. So Michael Sherman is now going to show you all the tutorials that we plan to implement today.
Okay. So we've got two tutorials ready to go here. One of them is showing a commercial client and a commercial base station. It's these little Netgear LTE USB dongles with our commercial AirHarmony base station. And then after that, we'll show a SDR based implementation. So let me switch over and I'll show how to actually do all of this in Orbit. So what I've already done is we have a reservation on the scheduler for the Orbit grid, and that's where all of these resources are that we're accessing. And then once you have the reservation, your SSH keys, oh, hold on, that's not showing the right picture, is it? Let me minimize this slide. 1 second. Is the console screen visible?
Yeah, the three windows in the console, three console windows.
Okay, yeah, it just hasn't updated my preview then. Okay, as long as we're good. Yeah. So in the window in the top right, I have a SSH session to the grid console where we're managing all of these resources from. And I'm following tutorials that the GENI page has linked to. So to start with, we're just going to bring up a client node. It's just one of these commercial hardwares with the dongle attached, and just put a basic image on there that has the requisite drivers to attach.
And by the way, you're now seeing the OMF framework in action. So we are literally imaging the node with the basic Ubuntu image, as Mike said, with drivers. Again, this could easily have been done with the GENI node. The only issue is that we would have to have a USB dongle attached to the node, to the GENI machine itself. In this case, we're just using one of the yellow boxes, which has that dongle attached, and as you can see from the text, it's node 7.1 in the grid.
So while we're waiting for resources, I might just jump in and also mention that the really nice thing about the OMF Aggregate Manager is that a majority of the work has already been done for you. All the requisite drivers in Ubuntu or other Linux-based OSs are already set up for you. So all you need to do is load images that already have everything built in. What we've also done is for the second tutorial, there are sample RSpecs which we can make public, which you'll be able to reserve resources on GENI racks, and also you'll need to reserve the LTE base station using the mechanism that I demonstrated earlier. But what it does is it just really lowers the barrier of entry into starting your research using LTE for either building applications or for actually understanding the protocol itself.
Okay, so I just turned the node on. It already finished pushing the image onto it with all the drivers, as Manu mentioned. And now we're just waiting for it to come up, which should be just a second. Well, a few tens of seconds. Okay, and we're in. And so first we're just going to load the 2 drivers needed for the LTE dongle. And so we're doing this manually. There's also a scripting language for controlling Orbit that has support for this, but we're showing the details here. Once the drivers are loaded, we actually just open a serial terminal to the device itself. Just treat it like a modem. And so what we can see here is it's already attached on boot up to our airspan base station. It's on band 41. It's got a 10 megahertz channel. So that information is visible in this highlighted line. So it's already registered, and you can see all the various low-level details. We need to unlock it to just allow us to issue a command. Steps are available just copy and paste level on the tutorial as well. So we've unlocked it, now we open the connection, and that response means that it was successful. The last 2 steps we need to do is clear the default route, because when we first turn the node on, it wants to use the wired network. We're going to have it switch over to the wireless. And then just run DHCP on the new interface and get an address assigned. So now with that, we've been assigned that .3.2 address on our wireless interface. And now we're successfully pinging that packet gateway mentioned before. And so now we've, via the OMF, provisioned this client node and got actual bidirectional traffic going through. Also have a iPerf instance running, and so we can do a little bit of benchmarking. So we're actually getting some reasonable data rates through, which is, to be expected in this particular case because we're running a commercial client and a commercial base station. Let me switch back over to the slides, and I'll show off the second tutorial case. And as part of that, we're going to disable the airspan base station, so that we can switch over to our software one. Yeah, so this is actually the REST call. Let me type that correctly. Yep. Base station successfully stopped. Verify that it is no longer connected. Okay. So make sure this goes through. And we are deregistered. So we've brought the base station down. And so now we'll bring up the software base station. And go back to the slides. So for tutorial 2, we're running a open air interface based base station with a split setup. So the remote radio head is running in the orbit grid, and it's connected via Ethernet and our layer 2 network to the baseband unit, which is running in the GENI rack and is provisioned via an RSpec that's available in that tutorial. And so that's all the baseband unit and the GENI rack part is provisioned via the GENI interface shown before. And then the Vault packet core is also available in GENI. And it's running on the layer 2 VLAN that's spanning the country. So it's on that GENI backbone. The remote radio head is provisioned via Orbit, and so we'll actually show that via that same console window. And so what I'm going to show is we're going to bring up the remote radio head, we're going to bring up the baseband unit on the GENI rack, and we're going to connect all of them to the packet core and get traffic running again. Something to note is we've actually got a portable remote radio head set up. The portable radio unit, portable ENB, and we have actually brought that to some demo sites. And so we can tunnel traffic back.
We will be bringing it to GENI Nice as well. So you'll be able to see this, the tutorial 2 as a demonstration at GENI Nice on December 12th.
But we can do this anywhere we can tunnel traffic back to the packet core, or with the split setup, anywhere we can tunnel traffic to just a compute resource that's got a low enough latency. So here we're showing it between our local GENI rack and local node. We can do it anywhere you have a compute resource and an RF node. Oh. So I've brought up a node that has all of the software, the open air interface software installed on it. I'm going to quickly build the remote radio head software. It's got a few scripts on there with some default configurations. But there's documentation for how to customize each of them to your setup. It's mostly just changing IP addresses and interface names. And then in the left window here, this is actually the node in the GENI rack. This is a bare metal machine that was provisioned via GENI. And if you load the RSpec we've made available, you'll have this configuration. And so again, this is just some pre-packaged scripts for this particular configuration. but the config files can be edited just by changing the interface names. We bring up the remote radio head first. We see that it's listening on the local interface. Over in the other window, we're bringing up the actual eNodeB and watch it start loading. And I should probably run that as root. That usually helps. So it spawned threads on all the cores, started running. We see here it's actually initialized the USRP and started pushing an image onto it. And now it's sort of waiting for a client to connect. And so we told that to run on band 25. We see that's now band 25 and 5 megahertz, which is what we've told it to do, but it's not quite associated yet. So I'm just resetting that USB modem to force it to reassociate. And we should see some messages start popping up as it associates. Yeah, all these blue messages, it should be coming up now. It was losing the context of the client and then setting it back up again. Okay. Now we're attached, online, and connected. We're on the cell IDs that we configured in the config file. We just run the same commands as before on the client. Kill the old DHCP session because that was left over. But we get the same address because the MME is held on to our IP for us. Because we're doing this ourselves, we haven't implemented the proper mobility and state handling. As before, we've got a connection running, but this time it's running via the software base station instead of the commercial one. Let's just be clear, the data traffic now is going from this top node to a radio, to a node and SDR that's near it over the wireless, and then over our wired backhaul to the eNodeB in the GENI rack in this window. And finally from there to the MME and the packet gateway, which are located on the GENI VLAN, and then from there out to the rest of the network.
Right, so while Mike runs the iPerf, another thing to highlight here is, as you can see, all the different components of the LTE network, which we showed very, very early on when I was trying to do the introduction. You can run all these components separately anywhere within GENI. So the context here is you can run them on the rack, you can run them locally, as long as there are VLANs that we've set up within GENI available to talk, available between these components. You can have them. You can have certain portions run locally and certain things run remotely, and that is another really, really neat thing, which I don't think any other testbed allows you a distributed way to run LTE experiments. So that's really neat too.
Yeah. So the two iPerfs I ran, the first one up here was running just straight to the packet gateway. And so that's running entirely within the LTE setup. This bottom one is actually run to a public iPerf server that's operated by Hurricane Electric. And so that's going all the way out to the WAN through the whole network. So what we see down in the bottom window is when we push the data rates, we actually can see it sort of start missing processing deadlines. And so you can see at a low level the limitations of the various components. And so there's a lot to be played with. There's a lot of work being done on optimizing all these various aspects.
Okay, so I guess that, excuse me, this pretty much concludes the tutorials. I mean, obviously we can talk more about all the components, and if people have any questions, we would gladly try to answer them.
Yvonne, this is Ben. I just was curious on the schedule, the scheduler for the resources in WinLab. There were several different types of resources, the grid and other nodes. Can you just briefly describe those? What resources are available there, and also perhaps I know that there are some similarities to PhantomNet. You kind of raised that. Can you tell us what's different? Compare and contrast what you have to PhantomNet?
Sure. So first of all, as you can see in the first column of the scheduler, this sort of lists the name of the resource, or what we call the domain. So grid is obviously the big orbit grid with 400 nodes, right? And so Mike is now bringing the status so you can see all of these resources. So the grid itself, and it will take a few seconds to populate, there you go, is showing you two nodes that we use for this tutorial, right? They're in green, they're turned on. And those are the only two that we use for the tutorial. All the others are turned off. The other resources, you can just bring it up so it shows tabs. Yeah, other resources are literally other domains which behave exactly the same as grid, yet they don't have that many nodes and they're in different locations. So outdoor is literally a bunch of nodes that are distributed throughout the buildings on this and other campus. And of course, unless you know where they are, you're bound to see all sorts of different behavior. Now, of course, we try to help people when they want to use the outdoor, if the main grid is busy or if they're having a particular experiment that's tailored for the outdoor network. We will let them use it. I mean, they can reserve it and try it, but if they want to know what's going on, they need our help with that. Sandboxes are way more interesting. Sandboxes are literally the same thing as a big grid, except that they have much smaller number of nodes. At least the sandbox is 1, 2, 3, 5, 6, 7, and 8, right? And typically they have two nodes, which are two physical yellow boxes. And for instance, sandbox 1 is interesting because it does have the USRP B210s attached to the nodes, which of course means that you can do the SDR based LTE experiment in sandbox 1. You don't need anything else. You literally use the sandbox 1 and two nodes in there, and you can run the experiment that we just showed before. And let's say if you don't have a GENI rack or you just want to do the entire experiment remotely. Now, SB4 is literally the same as PhantomNet. I mean, in other words, it's the PhantomNet was inspired by Sandbox 4 to some extent. We have 9 nodes that are plugged into a resource manager or RF matrix that allows you to dial the attenuation between pairwise between any of the 9 nodes. Now, there are 4 base stations attached to Sandbox 4. 2 are WiMAX and 2 are Wi-Fi. And just to give you an idea, if you look at the topology, I'm sorry, I'm just trying to find it in Sandbox 4. If you look at current topology, right, and I don't know nobody's using it at the moment, but it should show us currently how it's connected. So you can actually see that all the base stations are disconnected, and then all the nodes are connected, fully connected in meshed together. So obviously somebody was doing some experiment with their needed 9 nodes and nothing else. Mind you, there are no antennas, or there shouldn't be any antennas on any of the sandboxes. In other words, the wireless interfaces are wired together between the pairs of nodes, in this case between 9 nodes. Now, coming back to the resources, Sandbox 9 is also special in a sense that it doesn't have any wireless interfaces, but rather has only SDN-based resources, meaning 9 or 12 nodes with programmable switches on top of it and a bunch of net FPGA cards in them. So it's mainly used for wired type of experiments. But other than that, you can think of every one of these domains as being exactly the same. You have a console, you have a bunch of yellow nodes or other devices attached to it, and you can run your experiments as long as you don't need larger number of nodes on any of those. And the commands and everything else and the look and feel is identical. And of course, once a GENI user with a valid GENI account and wireless enabled logs into the Orbit site, they can reserve any of these resources on the online schedule. Right.
So one thing I would add, Ivan, just to really stress on the difference between PhantomNet, which for participants online who might not know what it is, it's a LTE testbed that's developed and is part of University of Utah. And what they have is they have a large number of resources, which, as Ivan highlighted for Sandbox 4, are in RF isolated boxes, and there are no actual wireless that it's not wireless per se, but the wireless interfaces are all connected to an RF matrix. So what it does is there's a very heavy focus on really understanding the LTE signaling and LTE traffic. What the GENI LTE deployment does is it extends that, and it also allows you, because we have the commercial grade hardware that's been deployed outdoors at multiple sites, it allows you to run applications on top of it if you really don't or really are not concerned with the LTE functionality or the LTE networking, but you basically require an application that requires backhaul access, or you're trying to do some sort of SDN or heterogeneous network where you are trying to do handoff or handover between different technologies such as LTE Wi-Fi or LTE WiMAX. So it's an addition. So that's sort of a difference. Hope that clarifies for you, Ben, the difference.
Thank you.
Were there any questions about the tutorials?
Yeah, so there is a chat comment that PhantomNet adapted SDN to their networks, and that is absolutely true. They have an evolve packet core where the different components of the evolve packet core are deployed on top of on different virtual machines, and the traffic is actually controlled using SDN concepts. So they have OpenFlow, and they have a different resource controller that controls LTE traffic using OpenFlow. So thank you for pointing that out. And if there aren't any questions, we will, as we said, post a number of resources for running these tutorials on your own. We will be demonstrating the tutorials at the GENI NICE upcoming event on December 12th. And please feel free to reach out to us through usual GENI channels if you require any help in running experiments over GENI. Thank you.
I have one further question. Can you give us an overview of some of the types of research that have been done on these resources? You know, what the outcomes have been and papers and whatnot.
Absolutely. So we've had a number of universities use it for different research purposes. I'll highlight a few. So one is Wayne State University in Detroit, Michigan, and they have a local deployment of LTE and WiMAX base stations that they use for vehicular network research. So basically, what they do is they use these yellow boxes and they put them in cars, and they're running their custom onboard vehicular simulator software. So they are capturing real fidelity data when the vehicles are driving down campus, and they are collecting that data, injecting that data via the yellow box, which has the USB dongles that talks LTE back to the base stations. And they're collecting this data, not just the onboard vehicle statistics, but also camera sensing data that's then aggregated on the GENI rack. And then they're able to do really, simulations that allow them to add high fidelity data that they've collected on the ground, as well as aggregating a lot of the camera feeds to build up 3D models of their campus, which they use for public safety applications. We have other research at Clemson University where they apply SDN concepts, again in a vehicular context, where these yellow nodes are running a virtual SDN switch, and then they run an open floodlight controller on top of it, which allows you to hand off traffic based on the interface. So if they're in LTE coverage, they use the LTE interface of the yellow nodes to send traffic back and process it. Or if they're in Wi-Fi or WiMAX coverage, they basically use those different channels. So most of these are application oriented. The Clemson University research is mostly focused on these new autonomous driving concepts of collision avoidance and collision detection systems. So they basically are using this LTE mostly as a communication medium for their research. And we also have Wisconsin that has a really cool project where they provide free internet connectivity on campus buses, and they use the LTE as a backhaul network. What it allows them to do, even though they're providing free internet connectivity, is they have really neat data about the control of how the LTE base station is working. So they're actually studying that to optimize how to actually do network placements or location of their LTE base stations. So pretty much all over the place, but hopefully that gives you an idea.
As we move more towards these software-defined base stations, research expands the capabilities of these deployments, expand significantly to run really serious software-defined radio-based experiments. And a lot of people are right now using Orbit, mainly because the remote radio heads are not yet readily available for anybody else, but could be, to do LTE unlicensed or LTE in different bands or LTE LAA deployments and tests.
Perfect. Are there any further questions? Well, open it up one more time. Well, I just want to thank Yvonne, Manu, and Michael for presenting to us today. Thank you so much. And